Hi, everyone. My name is Logan Rosen. I'm a software engineer at LinkedIn, and I'm here to tell you why you should subscribe to LinkedIn Premium. No, just kidding. I thought I was one of the vendors. I'm going to tell you about how we were able to get from alerts to insights by performing trace-based causation at scale. So to start off, my team is called Triage Platforms. And we're part of the observability engineering organization at LinkedIn. Our goal is to reduce the time it takes for engineers to resolve incidents on the site. We want them to understand why their alerts are firing and help pinpoint what the cause might be. And we're driven by a mission to help keep the site running so people can find jobs, connect to opportunities, do all their thought influencing, that kind of thing. And so it's really important that we keep the site running and healthy. So we have a problem. We need to find the needle in the haystack. And LinkedIn has a very complicated microservice architecture. We run hundreds, if not thousands, of services in production, all with different responsibilities, owned by different teams. And they're interconnected in weird ways. And it can be hard to pinpoint exactly where an issue is coming from when someone gets an alert. And what we've recently done is invested in making sure there's at least standardized alerting across all the different services. You sign up for a signal pack, similar to what you heard in the Netflix talk, and you get standard alerts for errors, latency, QPS, saturation, whatever else is relevant to your service. However, because we're signing up engineers for all these alerts, we need to make sure that they're equipped to figure out why they're firing and get to the root of the problem. And the issue could be due to a microservice that is way further down the stack. Think 6 hops down. Or it could even be a database or a network switch or any other variety of factors. So we really want to make it easier for people to find out what should they focus on to figure out why the problem is happening. So there have been some prior approaches we've taken to this. And the first one was kind of where we started when I joined LinkedIn back in 2016. It was humans scrolling through a lot of graphs and trying to figure out what patterns match up. And basically what we would do is we would plot, here are all of the golden signal metrics at each inter-service edge. However, doing this is very error prone. You easily, if you're sleep deprived, it's 2 a.m., scrolling, you might miss something, or you might even focus on a red herring that really has nothing to do with the issue. It also requires a lot of training. You need to know what metrics to look at and what indicators can help you understand why there's a problem. And especially as we democratize the operational role throughout engineering at LinkedIn, we've needed to make sure that we make it simple for people to do this without needing a lot of prior knowledge of how everything interacts. So a step above this is performing metrics-based correlation, as you might have done at your own companies as well. So with this, we feed in a number of metrics that we know can help us understand why a problem is happening. And it's more efficient and more reliable in finding patterns than a human scrolling through all these graphs. You can use techniques like Pearson correlation to find positive or inverse correlations that a human might miss. However, there are still limitations in this approach, as I'll show in the next slides, where I show a bit of a contrived example. Metrics will tell you about a specific component or how 2 different components are interacting. But what they don't tell you is how things are happening for an entire trace, or as we think about it, like an impact path from a back-end service all the way to a client application. So here's a bit of a contrived example of the limitations of just relying on metrics to understand what's going wrong. So let's say we got alerted for service A. Sorry, the legend's not super clear here. And it had a high error rate. We know that A calls B and B calls C. And all of their error rates actually match up pretty evenly during this impact period. So it would be a natural assumption that C is the place we should focus because the errors bubbled up from C to B to A. However, it turns out that this is not always the case. If we look at the trace cohorts, we end up with two segments. We have some showing errors in A and B, but not C, and some showing errors in B and C, but not A. And so the tracing data actually shows that you can't just bubble up the errors based on the relationships between the services. You need to see what is actually failing for the members. This is, of course, a contrived example, but we've seen a lot of real-world situations where the shapes of graphs match up, but the issues are not actually related. This can mislead engineers and waste valuable troubleshooting time. So we thought there must be a better way. And recently we've invested a lot in emitting distributed traces from our applications. But what we had failed to do so far is figure out a way to harness them for real-time issues in a way that's not super slow to query or expensive and allows us to easily pinpoint problems that are affecting people. So the way we've approached this, and after hearing the talk earlier today, I've realized this is kind of like a pug. We're doing aggregation before the traces even make it into storage. So the way it works is all of our traces are produced into a single Kafka topic. LinkedIn loves stream processing. Kafka was born there, and we throw stream processing at lots of problems, perhaps to a fault. Sometimes I wish the site weren't so reliant on Kafka. But in this case, we found a lot of value in this approach. And so we have a stream processing job that consumes from the topic and reconstructs trees using the parent-child relationships. So each message in the topic is a span, and it has a span ID and a parent. And so we're able to, in memory, construct a map that allows us to traverse the entire tree. We then look for chains of errors by performing a depth-first search. So first of all, we discard any trees that don't show any errors. They're not useful to us. Let's look at this example on the right. So we start at A, and then we look for if there are any children with errors. And so we find B. Then we go to B and look for children with errors and get to E. And then we hit our kind of stopping point where there are no children, and we can consider that the blame or the end of the impact path. And so we do this in near real time for every trace that we've gotten a head sample of. And currently we're doing a 20% sample of all the requests through LinkedIn. We then count these paths. So in this case, ABE would be considered a path, an error path. And then we record the trace ID as an exemplar, because what we'll see later is we use that in order to help with the debugging experience. And then we can also leverage any relevant attributes from traces in order to improve this causal analysis. So we can look at the specific response code, the error type, the data center, anything that's relevant, that we can store that and use that as a means of refining our analysis. So now I'll talk about how we harness and make sense of this data. So for the paths that we're counting, like ABE, CDE, et cetera, we take the counts and then produce new Kafka events with the paths, the counts, and the exemplars. And we keep around 5 exemplars per path, just to avoid blowing up these events with a ton of trace IDs when an issue happens. We then send these events over to Azure Data Explorer for storage and analysis. And for those who haven't used ADX before, it's a data analytics platform that's optimized for logging and telemetry use cases. So we throw all our logs there, our traces there, and then also this derived data set that I mentioned. So we have a homegrown observability UI that we built in recent years, and that's where everyone lands when they get an alert. They hit a big triage button, and they get the details of the alert, as well as a causal graph, if we're able to provide it, along with other insights. And so when they land on this page, it makes an API call with the context of the alert to get a corresponding graph. And the context can include the impacted service, endpoint, even method, because different methods and different endpoints have very different behavior. So if we just look at, let's say, service level or endpoint level data, we might end up misleading the engineer who's investigating the problem. The API then makes a query to ADX to find the most anomalous paths during this period. So looking back at this example, we can imagine maybe at this time we saw counts of 3 and 2 for these paths. In other minutes, there's some baseline error rate of 1 or 0, more, which would be better. And so we look for what is standing out the most as a chain of errors starting from the impacted service. And that's what we return to the UI. And then it looks something like this. We plot a causal graph, and I grabbed a real-world example here, but I had to mask the actual service names. And so you see this chain of impact going from service A down to service D. And what we allow the user to do is then at service D figure out what are all the relevant logs, who owns the service that I can escalate to, and even look at the sample traces that we collected in the pipeline in order to deep dive into what's going wrong. And then below, we added a prompt to allow users to tell us if we correctly identified the impacting service, because we know we're not perfect at this. We can get things wrong, and so it's useful feedback to get from people if they believe that the causation is incorrect. So now I'll talk a bit about how we built this pipeline. So we leveraged Go, and our team loves writing things in Go because of a few key factors. It's performant. It has great concurrency primitives. If you haven't used channels to do concurrency, I highly recommend you try doing that and playing around with it. And then you also get the benefit of static typing. So you get confidence in the code you're writing. It's more maintainable. Things don't random break in production, at least not from a typing perspective necessarily. So it helps us, make sure that what we're releasing is going to work properly and handle all the use cases with unit tests as well, of course. And so we're dealing with a lot of scale. As I mentioned, we're at a 20% head sample of traces, and yet we're still dealing with 8.3 million events per second globally, and these are spans. So we've really had to build an efficient pipeline so that we're not blowing through all our compute. There are a ton of efficiency and scalability challenges. We've also needed to perform partitioning of our topic by trace ID. And some of you may be familiar with this in Kafka. If you don't do any kind of special partitioning, your events can end up on any consumer host. So we had to make sure that all of the clients that produce tracing events are using the partition, the trace ID to determine which partition they go into. That makes sure that any single consumer of these events has all of the spans from within a given trace. And because these trace IDs have a pretty uniform distribution in how they're generated, we luckily don't end up with hot partitions. We have a pretty reasonable balance across our partitions in the topic. So you can see on the right side how this is structured. We start with the applications that are emitting spans through an OTel SDK. Those spans end up going through a fluent bit agent, which then produces the spans into Kafka. Those events then end up in the consumer, which decodes them, and that can actually be a huge slowdown. I'll talk about that in a bit. It then aggregates them and finds the paths, and then every minute we summarize and collect those counts, produce them back into Kafka, ingest them into Azure Data Explorer, and then hit that database via an API. So now I'll talk a bit about the challenges we faced in building this pipeline. So one of them is optimizing the pipeline to avoid bottlenecks. When dealing with this level of scale, any single operation can really cause the pipeline to fall behind. And we witnessed this with our first iteration of this. We had every application emitting to a separate Kafka topic. And we needed a job that was repartitioning everything into a single topic so that we could reconstruct the whole trace. Turns out that's super inefficient, especially if you're consuming from 1,000+ topics at once. So we had to re-architect the way we produce traces into a single topic. Another example is decoding the events, like I alluded to before. We currently use Avro when we produce events into Kafka in order to serialize them. And Avro has various implementations of libraries in different languages, and they don't have a clear reference implementation for Golang. And it turned out that the library we were using was super inefficient. So when we hooked up pprof to the job, we found that we were spending an inordinate amount of time of CPU just decoding these events. And that's not where we want to spend our time. We want to do it in the meat of the job, which is performing the RCA. So we had to switch to a different, more performant library that also allowed us to store the structs alongside the code and allow for more efficient processing. Another challenge has been measuring the precision of our pipeline. And this is a really difficult problem that we still haven't quite cracked. When we get alerts, sometimes they turn into incidents, but it's usually the minority of alerts because incidents have a certain bar of severity to be tracked centrally. And so we do have an incident data set we can compare to, but the other problem with it is it's compiled by humans. And humans are not perfect at recording accurate information in incidents, as I'm sure you're all well aware. So what we try to do to measure the performance of our pipeline, or the accuracy, is to compare our causation to what was recorded in the incident. But sometimes it could mismatch, and maybe we were actually correct, and what was recorded in the incident was not. So what we actually end up spending time doing is manually debugging a lot of the issues we find, trying to pinpoint the real cause, and using that analysis to improve our pipeline. Another area where we've had issues is getting user feedback on accuracy. So as you saw a few slides ago, we have this little yes or no prompt here for if we correctly identified the impacting service. It turns out when it's 2 a.m., you're sleep deprived, all you want to do is fix the problem and go back to sleep. You don't want to fill out like a mini survey about, were we correct or not? And so we get very limited data from this. So what we're trying to figure out is how do we incentivize people to fill in this data so that, because in the end, doing that will help them figure out their alerts better. But it's a tricky problem. I'd love to hear if folks have solved this at their own companies or with vendors. It's something we're continuing to try to figure out. So what does the road ahead look like? One, I talked a lot about error-based causation. We want to expand this to handle different kinds of symptoms and signals. One of these is real user monitoring. We've invested heavily in having client applications emit events when there are crashes, when people experience errors, when they slow down, etc. But right now, we're not hooking together the client traces with the server side. There's an active project to try to figure that out. And unsurprisingly, one of the hurdles we're running into is how do we bridge the actual Kafka events with each other without having a really expensive repartitioning job. So once we've been able to sort that out, we can expand our pipeline to handle these kinds of problems. Another area is latency. Currently, we rely on metrics for this, but they don't consider, the full path and the contributions of each hop to the overall latency that you might see in a front end or a client. And so we want to leverage our tracing data in order to improve this analysis. And basically what that means is just expanding the scope of our pipeline in terms of the fields we look at and the heuristics we use. Another area we want to look into is supporting deeper levels of blame. So right now we focus on our microservices, but databases can be to blame. It could be a bad host. It could be a network switch. And so we need to look into those patterns as well in our data and possibly have more counts on different dimensions so that we can have more granular output to the user about what we believe caused the problem. Also, as was mentioned the other day, traces don't tell the full story. They help you get to the point where you need to focus, but then you need to also look at other signals like logs. And so once we've pinpointed an area of focus, we then want to figure out what are the most anomalous logs or exception types that you should look at in that blamed service. That way, we're really minimizing the amount of querying and manual investigation that engineers have to do. There's also a bit of a pipe dream we've had, which is we can limit who gets paged. No one loves getting paged for something that isn't their team's fault or they can't really do anything about. Especially if we're able to get to high precision in our causation, we ideally want to suppress the alerts that are affecting the other services and just wake up the people who can fix the problem. But we need to get to a very high level of precision before we have confidence in doing that, because if we mess that up, that won't be a good look for our team, and we could end up having an external outage that lasts way longer than it should. And finally, we want to improve the anomaly algorithm. I mentioned before that we return the most anomalous path we find during that period, but there can be multiple contributing factors in an incident, and sometimes there are multiple things that are anomalous. But we need to figure out how to separate the signal from the noise, because like I mentioned, there can be a lot of baseline noise of errors that are always happening. And so we don't want to throw red herrings at people. If there was a brief blip, but it's actually something that's more or less expected or a known issue that wouldn't have caused this more significant dip that caused the alert. So in conclusion, Traces can be powerful for determining causation, especially if you have a complex microservice stack. You can leverage stream processing to do this in order to avoid costly queries in your database, where it might not be able to find these patterns as easily as you can when you're doing this in memory in near real time with all of the relevant data right there. And I also highly recommend leveraging Go for writing high performance applications. It's been a huge savior for our team. If we wrote this in Java, I don't think we would have been successful. And yeah, that's it. Thank you.
All right, we've got time for a few questions. Any questions? We got one right here, right in the back. Yep.
I have two questions. So first of all, this is really highlight. How do your consumers know a trace is completely done, or like how do you decide when to do DFS on a trace?
How do you know when your? Oh, sorry. Let me just summarize the first one first. How do you know when your trace? Oh man, I had it in my head. How do you know when the trace is complete? That sounds like it.
Yeah, great question. So we actually did a bit of tuning on this. So we started with our proof of concept by waiting 5 minutes, like a flat amount of time. Because the hope was that within 5 minutes, we'll get all the relevant spans from a trace. But then we hooked up some instrumentation in the spirit of observability and looked into how many traces do we get the full path within X number of minutes? We used a histogram-based metric. And what we found is that in the vast majority, it's actually in under 2 minutes that we get the full trace. And so we reduced the amount of wait time to 2 minutes, and we found that it's largely successful in capturing the entire trace. But it really depends on the latency of the calls through the stack, how efficiently you're processing from Kafka, that kind of thing.
And your second part of the question.
It seems quite common that a service might batch multiple requests and process them at a time, which causes the situation that different traces join together in the trace, another trace. And you mentioned that your Kafka topic is prediction by trace ID. And in this case, like the tree that have different joining trace might end up in different Kafka consumers, which means that you cannot do DFS like in a whole tree. How do you deal with that?
I'll let you summarize that for me.
So in summary, you're talking about kind of things that happen in batches. You have different trace IDs that might be linked together as part of a single, let's say, transaction. But because we're partitioned by trace ID, we can only look at one trace at a time. Yeah, that's definitely a limitation of this approach. Right now, at least with how people have been instrumenting so far at LinkedIn, we found that generally there isn't a lot of linking between different trace IDs. We might start to see that more often as people instrument like nearline asynchronous flows. But this has worked well so far. We do need to figure this out though for the client server linking that I mentioned before, because likely the client will have a different trace ID than the server. So we'll need to figure out maybe another level of partitioning. We were thinking about maybe having like forest IDs for all the relevant traces in a forest, and then we partition by that. But it's something we need to figure out for sure.
And I think the one right here. Yep.
Yeah, I was very confused by you're not getting feedback for the was it correct or not, but shouldn't the incident have a solution and therefore you can go back to did you get the solution through one of the UIs or did you find it some other way?
Yeah, so I guess the challenge we have is, oh, sorry. So the question was around why don't we get feedback? Like, shouldn't people be figuring this out through this UI and then recording that feedback? Is that accurate?
No, like the incident will have a resolution.
Uh-huh.
Therefore,
Okay.
did the UI give that feedback, didn't give that pathway or found in some other way?
Yeah, so the challenge is that not every alert is tracked as an incident. So there isn't like a closure procedure for every alert, only for what's centrally tracked. We might want to change that in the future, but we need to make sure that if we're adding this level of process, that it's not adding unnecessary friction and that we have buy-in from people that now when you get up in the morning, when you get paged, you not only need to fix a problem, but you need to record a resolution in the tool. We don't have kind of that expectation today, so it's something we would need to tell people to do, which they might not enjoy doing, but it might be somewhere we have to invest.
All right. Well, we're gonna go on to the hallway track for any additional questions, or again, reminder that the speaker channels are a thing. With that, let's give one more quick round of applause to Logan.